Good morning, good afternoon, good evening. Welcome back to chapter 22. We're talking about the path that the air takes that goes throughout your respiratory system. We just said that the air goes from your nose to your pharynx, to your larynx, to your trachea, and now it's going to go from your trachea into your bronchial tree, into your lungs. And this is the bronchial tree. This is a cast of an actual set of lungs. And you can see all of the branching, all of the intense branching that goes throughout the entire lung system. And to be fair, it's more like a bronchial bush than it is like a bronchial tree, isn't it? But you got the stem and then branches, and it branches. It actually branches 23 times, as in stem branches, that's one branching. This branch then branches, that's another branching. That's 1, 2, 3. It branches 23 times, 23 orders of branchings until we finally get down to those tiniest of air sacs called the alveoli. The alveoli, that is their entire job, is to do gas exchange. Their job is to take air in, allow the blood to pull oxygen from that air, and then for the blood to dump carbon dioxide back into the air. The alveoli are just little balloons, very thin-skinned balloons, that have a very thin-skinned blood vessel on the backside of it. Just imagine like a balloon that you put inside of fishnet stockings. That's basically what the alveoli are. The fishnet stockings are the capillaries, we call them, thin blood vessels, very tiny blood vessels. The balloon has air in it, and the blood vessels take the oxygen from the air and dump carbon dioxide into it. All of the alveoli, and you've got millions of these alveoli, all of the alveoli have tiny little cobwebs of blood vessels on the backside of it. As we said, the alveoli have very thin walls, simple squamous epithelial tissue. The blood vessels on the backside are also made of simple squamous epithelial tissue. So the entire respiratory barrier, the entire separation between air and blood is 2 layers of squamous cells. One layer is the wall of the alveoli, the other layer is the wall of the blood vessel. 2 little layers, squamous cell layers. We said a while ago that lining the interior air chambers of your lungs is a very thin film of water. The problem is, A, those chambers are tiny, microscopic literally. B, water has a really high surface tension, and what that means is water really likes to stick to itself. The surface tension of water is sufficient to collapse those balloons. C, blood can't take oxygen from air. It has to get it from water. So I have to have the water. So now I have a problem. How do I make it so that I can have the water in there so I can get oxygen, but not so that it collapses my alveoli? And the answer is a surfactant. Surfactants are made by what we call type 2 cells. The cells that make up the wall of the alveoli are called type 1. The type 2 cells are the ones that make this surfactant. The surfactant is made by type 2 cells, and what surfactants do is that they break the surface tension of water. Detergents are surfactants, and what they do is they make it so the water doesn't want to stick to itself as much. So that allows the water to make a much thinner film, so it does not collapse the alveoli. Very premature babies. I remember when I was a kid. When I was a kid and a baby was born premature, it was a big deal because the baby was going to have, the adult, was going to have respiratory problems for the rest of their lives. And the reason for that is because the type 2 cells aren't ready yet. They're not making enough surfactant. About 20-ish, 30-ish years ago, they started administering surfactants to the lungs of very premature babies. And now, preemies have far less incidence of lung disease when they grow up. Their lungs aren't ready yet. The lungs are fine. It's that the type 2 cells, the ones that make this surfactant, that break the surface tension of water, aren't working. So they have to administer artificial surfactant to very preemies. It's kind of a big deal. And it's a wonderful advantage, a wonderful advance that we're now able to do this to prevent a lifelong of lung trouble for these kids. Here we see again, here's my lung. We see that bronchial tree. We see the branching until we get out to these tiniest of branches. Just kind of imagine that these alveoli are a grape, a stem of grapes, except the stems are hollow straws, and each grape is a little miniature balloon. And so you can blow on the stem and it will inflate all the grapes, right? Well, here's my stem, and here's my bunch of grapes. On the back side of all of those balloons, all those little grapes, are a cobweb of capillaries. Capillaries being tiny blood vessels to be able to do the gas exchange. Each one of these balloons is an alveolus. These are groups of alveoli. Just think of them like a bunch of grapes made of balloons, where the stem is a hollow straw, so that air can be blown into, piped into the balloon. So just kind of imagine like an entire grapevine. The entire center of it is hollow. And if you can imagine that, that's an image for what the lung is like. The lungs in humans are paired, and in most animals are paired, not all. Snakes only have one lung. Though, as in development, they actually start off with two, but the right one stops developing, and just the left one continues to develop. Kind of interesting. Two lungs, they're paired, duh, and the right one is bigger. Why is the right one bigger? The right one is bigger because the left one has to provide space for the heart. And actually there's a cutout, and that cutout is called the cardiac notch. The right one's bigger and it has 3 lobes. The left one is smaller and only has 2. 98% of all of the oxygen carried by your blood is carried by this stuff called hemoglobin. Hemoglobin is a protein that we find inside of your red blood cells. 2% of the oxygen carried by your blood is actually carried by the plasma. Remember that blood is 2 major components, the red blood cells and the liquid called plasma. 98% of all of the oxygen is carried by the red blood cells, by hemoglobin, and only 2% is actually carried by the plasma, just dissolved into the plasma, dissolved into water. And what do we say? Water can't hold very much oxygen. That's why we have this stuff called hemoglobin. When the oxygen is bound to the hemoglobin, it's called oxyhemoglobin. Each hemoglobin molecule has the ability to bind 4 molecules of oxygen to it. Here we see a molecule of hemoglobin. Can you see the 1, 2, 3, 4 weird little discs in there? Those discs are called the heme discs, and I'm not sure if you can see it or not. Again, I hope you've got these PowerPoints saved. There's a little black dot, a little black circle in the center of each of these blue discs. At the center of each heme disc, the twisted spaghetti, that's the globin molecule. There's a heme disc at the center of each of the globin molecules. At the center of each heme disc is a single atom of iron. And you know that people often have to take iron pills, right, for their blood, because they don't have enough iron. They have what's called iron deficiency anemia. This is why. This is why you have to have iron for your blood, because you have to have iron to make heme. You have to have heme to make globin. You have to have both of these to make a functional molecule of hemoglobin. And if you don't have iron, you can't make heme. If you can't make heme, you can't make globin. If you can't make globin, you can't make hemoglobin. If you can't make hemoglobin, you can't make red blood cells. If you can't make red blood cells, you don't have enough blood. The tiniest little thing. This is why people need iron for their blood. 98% of the oxygen is carried by the red blood cells, and 2% is dissolved in the plasma. 80% of the carbon dioxide that's carried by the blood is dissolved in the plasma, and 20% is bound to the hemoglobin. It actually binds to a different spot on the hemoglobin than the oxygen does. The oxygen physically sticks right to that one atom of iron. We said that each hemoglobin can carry 4 oxygen molecules, 1 oxygen molecule per iron atom. All right. 80% of carbon dioxide is carried by the blood, 20% is carried by the hemoglobin. Thanks a lot. See you in chapter 23.